Welcome. So, if you've ever found yourself just staring at an integral in calculus that looks completely and totally impossible, you are in exactly the right place. Today, we are unlocking a seriously powerful technique that turns those monster problems into something you can actually solve. Okay, let's just dive right in. Take a look at this. This is the kind of rational function that just makes you question all your life choices, right? You know you can't use substitution. Integration by parts looks like an absolute nightmare. So what are you supposed to do? No, really, think about it for a second. This is such a common roadblock for students. But the solution? Well, it's surprisingly elegant. And it's not about learning some new, even more complicated integration rule. It's actually all about algebra. And that is the whole game right there. The technique is called partial fraction decomposition, and all it means is we're going to take that one terrifying fraction and we're going to smash it into a sum of simple, bite-sized fractions that are incredibly easy to integrate. So here's our game plan. We're going to start with the big idea, run through a supercritical first check, and then we're going to level up through the three main cases you'll run into. By the end of this, you'll have a complete toolkit for these problems. So how does this actually work? Well, the big idea here is that we can basically reverse the process of getting a common denominator. You know how you combine small fractions into one big one? Well, we're doing the opposite. We're taking the big, messy fraction and breaking it apart into its original, simpler components. Honestly, this is the perfect way to think about it. Just like a big Lego model, our integral is built from these simple individual bricks. And when we break it down, we're not left with a pile of junk. We're left with a neat set of simple fractions that are each incredibly easy to integrate by themselves. Okay, before we start breaking anything down, we have to do this one crucial check. This is the step that so many people forget, and trust me, it can send you down a completely wrong path. We've got to ask ourselves, is our rational fraction proper? And it really is that simple. All we're doing is looking at the highest power of x on the top and on the bottom. For this whole technique to work, the bottom polynomial has to be heavier, its degree has to be strictly greater than the degree on top. Let's just look at them side by side. On the left, you've got x plus 7 over x squared plus 3x plus 2. Highest power on top is 1, on the bottom it's 2, so the bottom is heavier, its degree is greater, it's proper. We're good to go. But on the right, the degrees are both 2. If the degree on top is equal to or bigger than the bottom, it's improper. And in that case, and this is important, you have to do polynomial long division first before you can do anything else. All right, so let's assume our fraction is proper. Now we can move on to level 1. This is the most common and honestly the most straightforward case. It's where the denominator is just made up of distinct linear factors. This is what you're looking for. See how each piece is simple, like x plus 2 or x minus 5, and none of them are repeated? That is the classic signature of a case 1 problem. And here's the 4-step battle plan. First, you set it up. You break it into a over the first factor plus b over the second. Next, you clear out the denominators. Now, step 3 is the really clever part. We use something called the zero method. Basically, we strategically pick values for x that will make one of our terms just vanish. So for a factor like x minus a, you just plug in x equals a. That whole term goes to 0, and it lets you solve for the other constant instantly. It's a super fast, really elegant way to find a and b. And here it is. This is the payoff. That complicated mess on the left turns into the sum of two ridiculously simple integrals on the right, and each of those is just a basic natural logarithm. See? This is the real power of the method, turning the impossible into something truly elementary. Okay, let's level up. What happens when one of those linear factors decides to show up more than once? This adds a little wrinkle to the process, but the idea is pretty much the same. This is the dead giveaway of a level 2 problem. You've got a linear factor, but it's raised to a power, like x minus a squared or cubed or whatever. It's repeating. So the setup, that's the key difference here. For a repeated factor like x minus a squared, you actually need a separate fraction for each power. So you'll have one for x minus a and another one for x minus a squared. You can still use that handy zero method to find some of the constants, but when you run out of easy x values, we bring in a new tool, comparing coefficients. This just means we expand everything out and then match things up. We'll say, okay, all the x squared terms on the left have to equal all the x squared terms on the right, and that helps us find the rest of the unknowns. And now for the final boss. This is definitely the trickiest case. It involves something called an irreducible quadratic. That's a quadratic factor in the denominator, like x squared plus 4, that you just can't factor any further using real numbers. You'll learn to spot these pretty quickly. They're the ones that can't be broken into simple linear parts. The classic sign is a term like x squared plus some positive number. Since there's no real number you can square to get a negative, it's just stuck as a quadratic. Now, the setup here is the single most important rule to remember. A simple linear factor just gets a constant a on top, but an irreducible quadratic factor needs a full linear term on top, bx plus c. Once you get that set up right, the strategy is kind of a hybrid. Use the fast zero method for any linear factors you might have, and then you switch over to comparing coefficients to hunt down the remaining constants, b and c. And there you have it. We've just gone from one single impossible-looking problem to a full toolkit that can deconstruct a massive range of integrals. Let's just do a quick recap of the essentials. So here it is, your partial fractions cheat sheet. It always starts with one question. Is the fraction proper? Once you've checked that box, you just identify the type of factor in the denominator, and that tells you the correct setup. Then for solving, the zero method is your go-to, your primary weapon. And for the tougher cases, comparing coefficients is that powerful backup you need. If you can master this flow, you can handle almost any of these problems they throw at you. You know, ultimately, the big takeaway from all of this goes way beyond just calculus. This idea of finding the simple, fundamental pieces inside a really complex system is a powerful way to approach any challenge, whether it's in math or engineering, or even just planning a big project in your own life. So, the next time you're facing some daunting task, just remember the Lego model. Don't try to solve the entire thing all at once. Instead, just ask yourself, what are the simple, manageable bricks that make up this problem? Find them, solve them one by one, and you'll find the whole challenge becomes much easier to handle.